Hello friends, welcome to Physics Online. So we continue with electrostatics, and today's chapter is electrical field lines and electrical flux. So what are electrical field lines or lines of force as they are called? So in order to visualize an electrical field, we take the help of electrical lines of force or electrical field lines. As the name suggests, these are imaginary lines drawn to depict the nature of electrical fields. So practically there is nothing called as electrical field lines. We are just drawing lines to visualize how the electrical field looks. To be very concrete, the lines are so drawn that the tangents to any point on the given line gives the direction of the electrical field at that point. So electrical field lines are such that if you draw a tangent to any point on the given line, it gives you the direction of electrical field. That is the formal definition of electrical field lines. Now let's look at some of the properties of electrical field lines. First of all, the lines start from a positive charge and terminate at the negative charge. That means electrical field lines will move out of the positive charge and will go into the negative charge. Lines of force never intersect each other for a very simple reason. If you take up two electrical field lines and let us say that they do intersect, so let us say that they do intersect, and then what happens? Then we will find that the norm tangent to the electrical field lines will give us two electrical fields, and these two electrical fields will be simultaneously appearing at 2 points. Let us say that this is one electrical field line and this is another electrical field line. So let us say it is intersecting here and we draw two tangents, one is here and here. So you see you get two electrical fields, which is not possible. So we conclude that electrical field lines do not intersect. Then the tangent to a line of force at any point gives the direction of the electrical field. So let us say that we have got an electrical field line like this, and we take a point here and draw a tangent. We take a point and draw a tangent here. We take a point and draw a tangent here. All of them give you the direction of the electrical field. So let's move on. So number of lines that pass through a unit area through a plane at right angle to the line is proportional to the magnitude of E. That is, when the lines of forces are close together, E is large, and where they are apart, then E is small. So it looks something like this. Suppose we say that we have got a line like this, and we got another line like this, and we got another line like this. So we draw a few lines, and we draw a few lines like this. Now you see in the first case what I drew, the lines were close together. So here the electrical field lines will be greater, whereas here the electrical field will be lesser. So let us say that this is E1 and this is electrical field E2. Then we can conclude that our E1 would be greater than E2. That is what is being said here. Let me write it. So E1 would be greater than E2. E1 would be greater than E2. So the number of lines per unit area through a plane perpendicular to the lines is proportional to the magnitude of E. So let us say that we take a surface, let us say we take this surface, and our electrical field lines pass normal to the surface. So they are passing like this, so they are passing at this point. So we say that let this be the plane and let this be the electrical field lines. So these are the electrical field lines which pass through this thing, And so if you take the number of lines that pass through unit area, that is proportional to the magnitude of E. Later on we'll try to understand what do we mean by electrical flux. So the point I just mentioned will be obvious to you. Which also states a very interesting fact that if you take a unit positive charge, then if it is in free space, it gives rise to epsilon naught lines of force. So if you take a charge over here and it is 1 coulomb, then the electrical field lines that come out of this 1 coulomb will be equal to epsilon naught. So the number of electrical field lines coming through 1 coulomb will be equal to epsilon naught. So if you have got Q, then the total number of electrical field lines emanating from it will be equal to epsilon naught into Q. Let's figure out this again. So let us say that we have a positive charge and it is 1 coulomb. So it is 1 coulomb. That is unit positive charge. Okay. So let's say like this. And our electrical field lines are going away from it. Question is, how many electrical field lines will be going out of this? The total number of electrical field lines going out will be equal to sigma. That means if your charge is 1 coulomb, the number of electrical field lines, will be equal to epsilon naught. So if your charge is Q, then the number of lines will be equal to epsilon naught into Q. Yeah. So let's go ahead and so see, when you have a positive charge, you notice that electrical field lines are going away from it. If you take a negative charge, then your electrical field lines are coming towards it. If you take a positive negative charge, electrical field lines go from positive to negative. If you take two positive charges, then the electrical field lines move away. There is no electrical field here. If you take two plates and give each charge Q, one positive and one negative, then you will get lines moving parallel to each other. So here we have given a charge Q. Here we are given on the top plate, we are given a charge plus Q. And at the bottom we have given a charge minus Q. Notice the electrical field lines are all parallel lines except at the end they are curved. So this is a uniform electrical field. Uniform electrical field simply means that the magnitude and direction of the electrical fields are same and all electrical field lines are parallel to each other. Now we come to get what is called as electrical field. So let us say that we have electrical field lines going like this and we have a surface. The blue color thing is a surface. N is a normal to the surface, perpendicular to the surface. If you take one electrical field line E and try to make a component, now remember the electrical field E and the normal make an angle theta with each other. N is a unit vector normal to the surface and capital E is the electrical field. Theta is the angle between the normal and the electrical field. Now, if you take the component of E about the normal N, then you will get it as E cos theta. Going further, we define electrical flux as through a surface in an electrical field as the total number of electrical field lines passing normal, means perpendicular to the surface. Thus, if ds is the flux, it will be equal to E cos theta into ds. That is, E cos theta is the component of one electrical field line multiplied by the total area. Now remember, ds is the area, theta is the angle and E is the electrical field. So notice over here we have given that we have turned all the things. Now here notice all the electrical points are perpendicular or parallel to N. So ds will be equal to E ds cos theta. So from the definition we get this. We do a little mathematical exercise. First we define ds as a new vector. We call it as a area vector, which is a scalar multiple of a vector quantity. The scalar being the area ds and vector being unit vector n. So if you look at the magnitude of the area vector, it will continue to be ds. But if you look at the vector, then its direction will be along n. Then we can say that the electrical flux d psi is the dot product between E and ds. And if you are looking at the magnitude, it would be equal to E ds cos theta. So we have come to the end of this session. We will see you next week. Please don't forget to subscribe my channel and share it so that it reaches many people. Next class I will be looking at electrical dipole and the electrical field arising due to it, and also the torque acting on an electrical dipole placed in an external electrical field. Thanks for now and take good care of yourselves.